So yeah, let's do this. I'm gonna let everyone unmute themselves, and let's go into our Q&A session. And again, it's Option Y on Mac or Alt Y on Windows. And now that I'm here and unmuted and you guys can see me, you may see me sneeze. Just to warn you, I may sneeze, but I think I've got it under control. So, you know, who wants to go first? Who has questions? Go for it.
Yes, and I'm afraid I had internet trouble, so I came in a little late, Riccardo. But very interesting work. My first reaction is yes. You know, the speed of light being faster than what it is now in the initial expansion of the universe is, you know, I regard it as a really necessary condition, given the fact that the CMBR is remarkably uniform across the sky. I mean, we have photons meeting each other at Earth that have never been introduced, supposedly, and yet they are reflecting the same black body temperature. And I regard this, and correct me if I'm wrong, is this sort of analogous to the idea that a gravity wave will go at the speed of light, provided the space-time is not being warped very strongly. An analogy is, you know, shock waves in hydrodynamics, where you have a sound speed, which is for small, which is obeyed by everything for small perturbations on the pressure. But if you set off a block of TNT, or better yet, HMX, then the shock goes as fast as it wants until it slows down.
Yeah, so yeah, same, a very similar thing. So if
very good, very good.
Yeah, very similar thing. So
it's a you know, I regard that as a one of the things that explains, well, I would enjoy your comment on the Albuquerque warp drive concept, where he believes he can kind of disconnect himself from space-time and be kind of a shock wave going as fast as he wants.
Yeah, look, I would disagree with that, because if you, what I tried to demonstrate in the presentation is in the Alcubierre situation. So, you know, if you put a pin through your spacecraft, so it's not moving because you're looking at it, it's not moving, but space-time is, right? What I try to demonstrate, so what I try to demonstrate is that the maximum that you can actually perceive space-time as flowing is going to be 1.1 C. So you can't go as fast as you like. You are cosmologically bound, and satisfying GR is not enough. So you actually need to be cosmologically compliant in your solution as well. And that cosmological compliance limit will be what looks like to you 1.1 C. But if you're standing on, if you somehow could be standing on the edge of the universe as it's expanding, that's where you measure C equals C. That's where you measure the definition of C. Everywhere else inside the universe, you're measuring, you're actually measuring a lower value. But even though it appears on your instrumentation like you're measuring C, that's because your instrumentation is inside the gravity well with you, right? So,
sure.
Yeah, and an important thing I just want to reiterate while we're on this point is the difference in perception between with GR, you're on the outside of and you're driving your problems and what happens in the situation. Within ecology, you're at the bottom of the, so there's a big difference. Hang on. So have I just lost you guys? No.
No,
No. I'm still here. Thank you very much for. I'll just make a comment. This sounds a lot like standard inflationary cosmology, where they
Well,
Only you're just saying, let the
Okay.
speed of light vary rather than some scale size of the universe. Whoops.
Yeah, I think his connection might be a little bit unstable. I think he'll be back
Gee.
though.
The key question. I'm just kidding.
Well, we'll give him a sec. This,
Riccardo, we lost you there.
yeah, Riccardo, your signal is breaking up, sir. Oh, and there he goes.
I didn't think my question was that crucial.
Yeah. Well, you know what? Let's keep the hands up. I mean, we can just chit chat for a minute. I'm sure that he will be back in.
There he is.
Is he back?
Looks like it. He's talking, but he's muted.
Oh, let me
All
ask.
right. Okay. Sorry about that.
Okay.
Yeah,
Perfect.
I don't know what happened there. Sorry about that. Okay. So we're good to go. All right.
Yeah. Okay. Well, John, did you want to ask your question again, or
Oh, I just a very quick question, and then I'll let everybody else ask. Do you consider yourself kind of this is an inflationary model?
No, it's okay. So I described cosmological inflation, yes, and cosmological inflation just dropped out organically.
Oh, okay, good,
right.
good.
So I don't care one way or the other. It just dropped out, and it happened to agree with the standard model of cosmology. That and everything else agreed with it.
Does this have anything to do with our embargoing our sanctions on the Russians?
No.
Pardon me.
No.
I shouldn't even joke about that. Thank you very much, Riccardo.
No, it's all good.
And John, thank you as well, sir. Let me go to Robert next. Robert.
Hey,
Sir?
Riccardo.
Hey, Robert.
Hi, Riccardo. I think I answered my question, but I thought I'd just confirm it. You chose lambda as a cosmological constant. That has nothing to do with the lambda particle, because that's a baryon as well.
Yeah. No.
Just they play, just a symbol on words on play.
Yeah.
Okay. Oops, and there goes our signal again. Well, at least he was able to. At least he was able to finish the presentation.
Yeah, well,
Maybe
that's right.
have him
Okay.
talk without the video part.
Pardon?
Maybe he can shut off the video so he has more data rate.
Yeah. Riccardo, would you like to try that? You want to try shutting your video off?
Yeah, I'm just going to try something else. Just 1 second. Let me just. You might lose me here, but it'll only be for a moment.
You know, I almost wonder if it might be Wi-Fi interference. Maybe I shouldn't admit this. I'm old school. I still use Ethernet. I don't trust Wi-Fi. I mean, I use it all the time for everything, but
Yeah.
I'm hardwired for this stuff.
Let me just.
Yeah, Ethernet's super reliable compared to Wi-Fi.
Okay. So I might lose you just in 1 second. All right. Okay. Have you got me or not?
Yeah, no, you're still here.
Okay. All right. Well, hopefully this will give me a higher data rate.
Okay. Well, yeah. So did you want to respond to Robert's? I think Robert, you were just asking about the lambda term, right? But I think that's just a term.
It's just a symbol on word. Symbol on play. I just wondering. I think
Okay.
Coincidence.
Why don't I go to Michael next?
Yeah. Okay. We're good. So that should have fixed it. I think. I hope.
Okay. Michael, sir. Did you have
All
a
right,
question?
sure. So my thought was, you mentioned the justification for a maximum warp field speed
Yeah.
is because you could cross the cosmological event horizon and escape the universe. But I mean, doesn't the like cosmological expansion constant already violate conservation of energy anyway?
No.
Why not? So you have
So
dark
hang on.
energy and you have this energy per unit area, like volume, that
Yeah.
is being inserted over time or removed.
I'm sorry, Michael. I don't kind of follow.
So having a non-zero cosmological constant, having an expanding or contracting universe already violates conservation of energy, because all of your photons in your universe gain a small amount or lose a small amount of energy over time as that
No.
expansion or contraction happens. Yeah, you have got red shifting or blue shifting.
Yeah, but that doesn't violate. So you're saying it violates what?
So when you have expansion of the universe, or you have a accelerated expansion of the universe, your photons are red shifting over time. That's why the microwave background is microwaves instead of visible or something.
Yeah, and that violates what?
So that the energy of those photons has changed over time. They've lost energy as they've propagated all that distance through the universe. So that already, it violates conservation of energy over time in long. So why would we?
No, that energy that's being lost. So you're saying, because I just want to understand what you're trying to communicate, that energy being lost by a photon means that the law of conservation of energy is wrong.
Well, no, I'm saying it's being violated in that for the cosmological constant in general relativity.
Yeah.
If you have redshifted light at a distance, it was emitted with a higher energy and then it got redshifted, and so therefore it lost energy.
It's
so that violates.
Stretched. No, it hasn't. It's been stretched, right? So that photon's wavelength has been stretched, physically stretched over time. So there's an energy drop as we measure it, yes. But you're saying that violates. I don't understand. What?
So, well, I guess the more important question is, so why do you assume that nothing can escape the universe and therefore bound warp drive based on that?
Okay, so all right. Okay, it just, to me, right? Okay, my first bit of, I'll call it evidence, right? The first bit of evidence is just the escape velocity equation. So square root of 2gm on r, right? When you plug in my calculated value of cosmological mass and my calculated value for the Hubble length, right, which is my r. If you remember the circle that I might have drawn, that I drew in the detailed section, I draw a circle. It's got a radius of the Hubble length, right, and that's 14.57 gigayears, right? Now that's a value that I calculate. The standard model of cosmology value is almost exactly the same as mine. Now, if you draw a circle of radius r, and you calculate the circumference, you get all the standard model of cosmology values, right? But the point being, when you plug that value of r into the escape velocity equation, you come out with the exact solution is c, the speed of light in a vacuum. So that's the escape velocity for our universe. So that's the first bit of mathematical evidence that I provide. The second bit of it.
If we could pause there, if you can hold that thought. So that also assumes that all of the observable matter in the universe is all of the observable matter, and that there's nothing outside of that's not observable. Because if there were additional matter outside which we can't currently observe, then there would be no net gravitational fields. It would not be isotropic. I mean, it would be isotropic. So you wouldn't have an escape velocity associated with that, because there's no well, so to speak. If matter just keeps going on infinitely.
Agreed.
But yeah, go ahead.
Yeah, agreed. So you picked up on an important point, absolutely, and I should emphasize that. What I'm suggesting is the only assumption that I can make is that what is beyond the observable universe does not exist. There is nothing. That's the only logical assumption anybody can make, because any other assumptions, I can come back at you and say, you're wrong. Outside that boundary are unicorns and puffy clouds, and I would be as accurate and as correct as the person saying it's something else. So the only conclusion anybody can make is what we can actually observe. Anything beyond that, there's nothing. All right. So that's, you picked up on a
Don't
really
forget
good
the
point.
dragons out there.
And the dragons, that's right. And you picked up on a really
There
good
be
point.
dragons.
That's right. There be dragons. That's right. It's a good point. Now, coming back to the second bit of, well, I call it evidence. It's not really evidence, it's more of an opinion. Why we can't escape the universe. Now, why we can't escape the universe, in my view, withstanding that first bit of mathematical evidence, is that, to me, it just doesn't make any sense that we would be able to escape the universe. Because if we did, it would break physics, because that means the law of conservation of mass and energy, well, it's wrong. And look, I don't know, it's maybe it's religious, but I believe in it.
So if there were counterexamples then to the laws of thermodynamics or laws of conservation of energy, then
Well,
you'd have
then
to rethink all bets are off then.
I would have to rethink my position. Yeah, absolutely. Yeah, no doubt about that. At least the escape velocity conclusion, at the very least that.
I can see Michael he's thinking about stirring the pot. Look, see that smile? See the smile? He's like,
Actually, I'm actually good for now.
Smile.
Okay,
I'm just thinking.
Well, thank you, Michael. So
Yeah,
let's do this. Let me go to Harold Tavares next, then.
Oh, thank you. That was a great presentation. You gave a lot of beautiful, good information. Now, looking at my note, I want to ask you one question. Since I noticed you're using the speed of light to determine, the observable universe, the speed of light, and it looks like you assume that, you actually show that the speed of light actually is variable, have been variable throughout the cosmological history of the universe. And since the speed of light depends on the permeability and permittivity of the space-time. Now, are you assuming, in your model that the speed of light was variable in the past? Are you saying, is it variable in your model today, or is it just constant to what we measure the speed of light to be today? Because you throw some numbers there, making it look like, it's no longer it change, or would it change in the future?
Yeah, correct. So yes, the speed of light has been changing since the Big Bang, and it has gone up and down, right?
Okay.
The last time when the speed of light was actually the speed of light was when the universe had an age of 7.3 gigayears, right?
Yes.
And it also, that C equals C point also coincided with when the cosmological constant equaled 0. And that also coincided when the dark energy density parameter equaled 0. So what that means is that instantaneously, right, all of space-time everywhere at the same instant was more permeable to light than what it is today. So for us now, in a gravity well, in the bottom of a gravity well, the speed of light is 0.84 C relative to what it was when it was 1 at 7.3 gigayears, right? But that speed of light now, 0.84 C, has an upper ceiling of 0.92 C. So that upper ceiling is that ceiling it's limited by dark energy, right? Because the dark energy field is not a massless field, right? A big chunk, 67% of the universe's mass is in that field, and the mass in that field is impeding the progress of light. Right. However, if we measure the speed of light in the laboratory with our instrumentation, our rulers and clocks have all shrunk, right? They're all scaled with the speed of light because we're sitting at the bottom of a gravity well.
Yeah.
So yeah, that's it.
Okay, on your slide number 8, I notice you point out that at one time, the speed of light was 1.37, et cetera, times 10 to the 38 than what it is today.
Correct.
Now, looking at the observable universe, the length will be 91.53 billion years. So what would the speed of light be, let's say, after the observable universe? Would it be higher? Because outside that limit, it seems to me like the permeability and permittivity of that space-time outside that length will be much lower, therefore the light would increase. What do you think it would be according to your model of analysis? Would it be higher, lower, or the same?
Okay, it will be, so in the region that you're talking about that we can't observe, that's outside our universe, the speed of light in that region, in true nothing, the speed of light will be exactly c. It will be the defined value of c, because that's how we've defined c. So c, as I mentioned, is the speed of light is no longer a measurement, it's now a definition. That definition's been given a number, and that number is associated with very specific conditions. So it's going to be totally flat space-time manifold for that number to apply. But everywhere in the universe, it's not a flat space-time manifold, it's a curved manifold. Some places curved more than others, like black holes are curved more than here on Earth, right? So the only place where C actually equals C, which is the definition, is the region that you're talking about. And that will always be the value, because that's where it's defined.
Okay. Looking at that answer that you gave me, thinking about it now, it seems to me like you are defining the universe from your analysis that it is equal to, that is the infinity, that is an infinity, and those are the limits. Now, that's your model describe it, fitting, more like it is an infinity, like the standard infinity, or would it be like a transfinity, like George Cantor, an infinity within an infinity? But the model would be that even if this infinity with the values that you have now expand into the next infinity, like if it was a transfinity, an infinity with an infinity with, the mathematician, Cantor, would that be it, an expansion into the next infinity? It would all be the same. Is that what your analysis?
Yeah, actually, you've asked a really good question there. I've got to tell you. Okay. The answer is, okay, and I might one day do a presentation on this, but I've actually developed that model. My model can be expressed in cyclic cosmology, and that's what you're talking about. One infinity moves into another infinity. So yes, and so yes is the short answer. So I go for the infinity becomes infinity becomes infinity. I go for that description, and that's cyclic cosmology. What I show in my work already, and if you know how to read my algorithms, I could point it out to you. But what I actually show is that when the very last photon, the very last photon expands, gets stretched to a certain point, to a certain length, if you like, it snaps, and at that instant you've got another Big Bang. So my work very much supports Roger Penrose's position on cyclic cosmology. Absolutely, yeah. So yes is the answer to your question.
Well, and Harold, thank you, sir. Let me go to Michael, because we're starting to get down to the wire before John comes on. So, Mr. Boyd, go ahead, sir.
Hello, can you hear me okay?
Yeah, hi, mate.
Hi, so I got 3 questions. The first question is speed of light. I'm kind of confused about what you're saying about being in a gravity well when we're talking about the speed of light. Are you suggesting that the speed of light is different on the surface of Earth than it is in it is in outer space, for example?
Absolutely.
Are you
course it-
saying the speed of light is less or more on Earth?
Okay, so on Earth, the speed of light is reduced. So look, I'm very much a proponent of Puthoff's PV model, right? So yes, the speed of light is slower here on Earth than it is in free space. But our rulers and clocks are scaled, so we measure it as C everywhere, but it's not. It's actually different.
So when you make a measurement of the speed of light in outer space, say on the International Space Station, and they come up with the same speed as they do here on Earth, you're suggesting that's due to the time and the length being different?
Yes, correct. Things are scaled accordingly. So our rulers and clocks are scaled accordingly. So that's why we always measure C as being C.
Okay, so are you also suggesting then that the space-time medium is different depending on where you are located in our universe?
Absolutely. Right. So let me, you've touched on a really good point there, and I'd just like to describe that. So everywhere in the universe, you've got the 0 point field, right? It becomes the polarizable vacuum field when you put a lump of mass on it, right? So like the Earth, right? So you transform the 0 point field by doing so, by putting the Earth there, you transform the 0 point field to the polarizable vacuum field. So what that means is, in a completely flat space-time manifold, you've got no matter in a universe, just the 0 point field, right? So you've got all these virtual particles popping into and out of existence. What you have in such a fictitious universe is you have an infinite spectrum. So the 0 point field is infinitely broad. You can have any manner of frequency there that you like, from very low to very high, right? In a universe with no matter, just a 0 point field, right? When you take our universe, for example, and you look at that, what you find is the 0 point field in the location of Earth is compressed. So when you put a pin in the Earth and you look at what happens at the cutoff frequency as you move out, what you find is this. You find as you move out, the cutoff frequency actually decreases from the surface of the Earth to whatever distance out into space. So your cutoff frequency actually decreases. But what happens is the number of modes increases. So what mass does, mass compresses the number of modes in the 0 point field spectrum from a very large number down to, in the case of a Planck particle, it converges that entire spectrum down to one single mode, right? One frequency.
One single what? Mole?
Mode, frequency.
Oh, mode.
Yeah.
Okay.
Frequency mode, right? So you've got this inverse relationship. So as you move out into space, your cutoff frequency for that spectrum decreases, but the number of modes in the spectrum increases. When you from outer space move towards the Earth, what you calculate is that the number of frequency modes in your spectrum is shrinking. It's getting smaller and smaller and smaller and smaller, but your cutoff frequency is getting higher, right? So yes is the answer to your question. I would absolutely.
So basically the energy is the same then. You're just changing frequency and wavelength, correct?
When you say the energy is the same, what do you mean?
Well, wavelength, when you measure a wave energy, You measure the frequency and the wavelength and the
Yeah.
amplitude, correct?
So well, yes, but so if you're talking about
So the energy, the amount of energy is the same, but the frequency and the wavelength are changing depending on where it's at, essentially.
yeah, right. But see, look, just on the amount of energy, I'm not sure.
That kind of segues into my third question to you, which has to do with what's referred to as offset spatial divergence, which is essentially, to travel in space is to travel in time.
Yeah.
So
Right,
if
so-
you are, for example, if you travel at a tenth the speed of light and you go for 2 light years away and come back to Earth,
Yeah.
everybody's going to be dead
Yeah.
because of offset spatial divergence. So
Yeah.
how do you account for this many body problem in your hypothesis?
Okay, I don't understand the question. Can you rephrase it, perhaps?
Well, I think you were getting at it.
Look, I totally get time dilation effects, right? I totally get that, but its relation to the many body problem, I'm not sure.
Well, there's not just time dilation. There's time.
Yeah.
Time can get shorter as opposed to longer, depending on if you're going in an accelerated frame. You can basically it's like expanded space time in Albuquerque's.
Well, and guys, if it's okay to mention, we're starting to push into John's time. So
Yeah.
Okay. So that's my question now, is about offset spatial divergence. If you don't think you can answer it, that's fine. I appreciate your answers so far. I was following you pretty well.
Good man. Thanks for that. Appreciate it.
well, thank you as well. So let me see, Robert, if you can go quickly, let's do that,
Oh.
and then
Thanks, Tim. I think this is quick. We know that speed of light changes through certain materials, hence
Yeah.
the bending of the beam. Can your theory describe that phenomenon, or at least applied, or the philosophy of your theory?
Absolutely. In fact, you've raised a good point, because all of my work's based on the polarizable vacuum model of gravity by Harold Pohoff, and that's an optical model of gravity. So it treats a gravitational field just like a lens. So it ties in exactly with what you're talking about. Absolutely.
Thank you. Thank you very much.
wonderful. And Robert, thank you as well. So let's do this. Let's go to gallery view here. Everyone, please. One more big applause for Mr. Riccardo Storti. Sir,
guys.
thank you. Thank you yet again. Thank you yet again. And I should apologize for cutting things short. A little bit of chaos today. But so what I'd like to do next is I want to introduce our next speaker, Mr. Dr. John Brandenburg.